All right. And what we're going to be doing today is we're going to be continuing along with our discussion of electromagnetic radiation, a special case of which is light. And hopefully I've been sharing with you my animation that is a traveling wave. And if you remember right, we said it's sinusoidal or cosinusoidal in shape. A traveling wave has two pieces. It has an electric field, and that's the yellow thing that is oriented in this particular case on the y-axis. So it has only a y component as drawn here. It can have any component, but in this particular case, it's got a y component. You can rotate it around. But once you rotate it, you'll also rotate the accompanying magnetic field, which in this case is in the z direction. And you see those two propagate, we say, together, bouncing off of each other in a sense, because a changing magnetic field creates an electric field that's changing. The changing electric field creates a magnetic field. Changing magnetic field creates an electric field, and on, and the wave moves forward, in this case, in the x direction. Okay, so that's what we're talking about. Look, we're up to 11. I want to look at, okay, that's the physical picture of the model. I'll stop sharing that with you. And we'll start sharing my PowerPoint, and we'll pick up where we left off. And I got some additional comments because I was rushing at the end yesterday to get this all in. We'll go to that. Good. And there's a couple pieces. Let me put this away, at least move it out of my way, and get myself a pen to write with. Okay, we said, much like we had in physical waves traveling on strings or springs or water or anything like that, we've got something called a wave equation right here. And you may or may not have enjoyed me going through on Wednesday, figuring out how that thing comes to be out of Ampere's law with Maxwell's correction, and also from Faraday's law. Those two couple together to create this equation. If you like that, that's good. If you didn't, that's good. That's good too. I'll never ask you on an exam to rederive a wave equation, for example, but you should recognize that they exist in science. They existed for mechanical waves. They exist for electromagnetic waves, like we're talking about for the rest of the semester here, the last couple days. I also teach a quantum mechanics class. There's a wave equation for elementary particles, electrons, protons, putting them together into atoms. There is a wave equation. It's called Schrodinger's wave equation. These things exist in science. And this is one that's fairly simple. We can look at it because simple in a sense that whether you know how to solve it because you've had Dr. Hamilton's class that looked at this, at the very least, I can inform you of some heresy about differential equations. It's a course where you guess at solutions, or you learn solutions, and then you check to see if they're right. Okay, it's almost like the first time somebody told me how to solve a quadratic equation by factoring them. So I'm going to guess at some factors until I finally get it right. And if it works, then that means I've got a solution. And the algebra teacher shook his head and said, yep, that's pretty much how it is. You play around with those factors until you get a set that give you the quadratic equation that you're trying to solve. And from those factors, you're able to get a solution. Differential equations is another branch of mathematics where in many cases, you're guessing at a solution. Now, they'll give you techniques on how to make pretty educated guesses. But at the end of the day, you've got to come up with a solution from one of these techniques. And often it comes down to guessing and then seeing if the guess makes physical sense. But then more importantly, when you take the guess and you plug it in, does it work? And so there was what we call a trial solution. That's a fancy mathematician word for it's a guess. Okay, we're trying this. If it works, we're going to go with it. And if we think that waves, because we've seen them in the physical world, are sines and cosines. We talked about harmonic waves back at the beginning of the semester. It's not a bad guess to think, if you believe that electromagnetic radiation is a wave, that it would also be sinusoidal or cosinusoidal. By the way, these are the big questions of the mid to late 1800s. Is light actually a wave? And Maxwell theoretically came up with what we went through in class on Wednesday, and said, yeah, it is a wave. I can show it with some equations, and that's what we did. You should recognize that there were a number of other people with an alternative view of what light was in the mid to late 1800s, and they pushed back all the way to no less than Newton, because Newton's idea, he looked at light back in his day in the 1600s, and he thought light was a particle. He referred to light as being a corpuscle. It's like a piece of blood or something like that. It's the same word, I guess. And so there is this dichotomy, I guess, this kind of tension between, is light a wave, because we've got a wave equation and we think it's sinusoidal, or is it a particle? And how do you decide whether something that you can't see is a particle or a wave? And the answer is, you look at what it does. Right? That's what does this thing do? Does it reflect like a particle? Does it bounce off of something like a particle? Does it have momentum like a particle? But there are things that like waves do. We talked about interference, where you get superposition, constructive interference. Does light do that? And the answer, unfortunately, is it does both of those things. It does what waves do. It interferes. It has constructive and destructive interference, and yet it reflects, which is something that a particle does. Like a billiard ball off the rail in a pool table. It reflects with exactly an angle of incidence equal to an angle of reflection. And we'll talk about that next week. So what is light? Right now, we're looking at that aspect of light where it shows where it does not show particle-like properties, where it shows wave-like properties, and that's what we're doing. Okay, so the question is this trial solution, is this guess right? And I ran through this really quickly. You have to take a second derivative of this solution with respect to x, and a second derivative with respect to time. And I just jumped right to the second derivative. I see people trying to do that in all the classes I teach. I'm here to tell you, failing something like Wolfram Alpha, where you just tell it, or Mathematica, or I just found something this year, a program called Maxima, which is like Mathematica, only it's free. So if you're ever looking for something like that for some of your research, I would recommend a program called Maxima. It's the same thing. Anyway, but I see people doing work where they just try to take the second derivative in one step, and I can't. Okay, so let's do that here. And by the way, if you understand a little bit about derivatives, just the notation of them, because this electric field varies in both position and time, that's the domain of multivariable calculus, which I recognize that many of you haven't had, but it's okay. All I do when I take the derivative with respect to x here is I just hold time constant. I hate to ruin a whole semester's worth of work, but that's what multivariable is going to boil down to. A lot of other stuff. But before I can get to this second derivative, I better take the first. And as I said, I'm taking the derivative with respect to x, so that time is constant. I just got to take the derivative with respect to x. So I bring the constant out front, and hopefully you all know that the derivative of the sine is the cosine. Okay, and then I've got the chain rule. I got to write what's inside those parentheses. By the way, just like we did with harmonic motion, oscillatory motion, and when we talked about mechanical waves, this piece right here in the parentheses, I refer to as the phase very often. And you'll hear me talk about that probably on Monday. We'll talk a little bit about phase, being in phase or being out of phase. Okay, it's kx minus omega t. That's the phase term. Okay, in any event, chain rule says, what do I got to do? I got to bring out, I'm taking a derivative with respect to x. So I got to bring out that k right there. Omega and t, those are constants. So when I take that chain rule derivative, nothing. Okay. And now to take the second derivative, well, I take the derivative of this again, and hopefully you can see I write the E0. The derivative of the cosine is minus the sine. Okay. And I just said minus the sine. So I wrote sine kx minus omega t. Also use the chain rule again. So I bring out a second k, and that k becomes squared. This time I wrote it out front. Okay. Similarly, if I'm taking the derivative of this electric field with respect to time, it's a very similar process. Okay. You can't just jump right to this, although I see people try to take the second derivative. Don't make me tell you my Good Will Hunting story again. We just don't see it. We work these things out. All right. So in any event, I take the derivative of the electric field with respect to time, constant again. That could be 3. I'll show you an example here in a second. Let's see. Derivative of the sine is the cosine of kx minus omega t. K is the wave number. Don't forget that. Omega is the angular frequency. It's related to the frequency f in hertz. Okay, and just like this before, I took the derivative of sine, I got a cosine, but the chain rule says I have to take the derivative of that with respect to time, and holding x as a constant, so I bring out the minus omega which is the coefficient of t. All right. And then when I take the derivative again to get to the second derivative now, the derivative of the cosine is minus the sine. Let's see. And then so I wrote down E0. I went back to sine with a negative, okay? And then let's see, I have to do the chain rule again, so that brings out another minus omega. Well, minus omega times minus omega is omega squared. It's positive definite, but I still got that negative sign from the fact that the derivative of the cosine is minus the sine, so I still have that out. And so that's where these two derivatives came from, okay? And then I push them into my wave equation to answer the question, are these two things equal with the appropriate constant? And I guess if you shove them in, they can be equal. It's possible. I can cancel that. The amplitude here cancels, okay? I don't have to worry too much about that. I don't want to cancel it because that's division. Division by 0 is not allowed. It is possible that those two signs can be 0, but their coefficients have to be equal. And so minus k squared has to be equal to minus mu 0 epsilon 0 omega squared. And so I guess the first thing I might do is get rid of the negative signs because it's on both sides of the equation. And I chose to solve for omega squared over k squared because I recognized when we talked about traveling waves, that was the velocity squared, okay? Velocity is equal to wavelength divided by period, which is equal to frequency times wavelength, because period and frequency are inverted. And if I multiply by 2 pi over 2 pi, I do indeed get omega over k. So if I was to give you a function, whatever shows up right here divided by whatever shows up right here is the speed of the wave. And here's the big deal though. You don't get to have any combination of omegas, angular frequencies, and wave numbers k, or wavelengths and periods, or wavelengths and frequency. The medium, in this case, free space, air, vacuum of outer space, that's what defines the wavelength. I'm sorry, that's what defines the speed. So if you pick a wavelength, there must be a defined frequency. If you have an antenna that creates a particular wavelength, for example, it will have a particular frequency based on the fact that the speed of light is governed by the material that the light is traveling in. And we'll see what happens next week when light travels through things other than free space. Okay, when it travels through say glass or some other transparent material. Okay, I want to work out a little problem here real quick. I think I have time for that today. We're going to be spending some time talking about the energy of these waves, these electromagnetic waves. So let's talk a little bit about what we can do with it. And I think one of the points, if I give you, and I said general will give you the electric field, but not always, okay? Let's say that you have a Z component, that thing that I had started, it was animated at the start of the class here today. Let's say I had an equation like this, and that's 0.05. That's a pretty big magnetic field. Tesla, that's the amplitude. That's what I would call like B0, right? And it's the amplitude in the Z direction because that's what I'm writing there. It's the Z component. And then I had, say, a sine, because I think that's what I started with. And then I wrote kx minus, actually this time I went plus, and hopefully you realize that just changes what direction this wave is going. And then I'll have something like 9 pi times 10 to the 8th radians per second. And as soon as I write that for omega, remember, if you're ever doing a problem with this, what units do your calculator have to be in for angle? And the answer, as soon as you see something like that, and the key often is look for the pi, because that tells you it's somehow related to radians per second and then times time. And you have to identify the parts here. I already said that's the amplitude, the magnetic field, which is fairly large. Hopefully you realize that must be the angular frequency right there, right? And so I think this, if you recall from traveling waves, means the wave is moving that direction, in the negative x direction. If that's a negative sign, it's going that direction. So that's kind of a rule that we saw in traveling waves that were mechanical waves, waves on a string. The same thing applies here, okay? And if you need a little refresher on why that is, I can actually show you a plot where I change that sign. One wave goes one way, one wave goes the other. I think I showed you that back when we were talking about traveling mechanical waves. In any event, I think that might be the first question, and we've identified the pieces here, okay? And so if somebody was to say now, how what's what's the wave number here, or the wavelength? Because remember, K is all about the space pieces, the wavelength, how long this guy takes to repeat in it. If I took a snapshot of it and I was able to somehow see the wave, which you can't, but how big is the wavelength? Okay, and how big is K then? Because they're related. What we said was that the speed of the wave has to be related to the physical constants, the permittivity of free space and the permeability of free space. And I showed last class, when you plug those numbers in, son of a gun, if you don't get 3 times 10 to the 8th meters per second. And I thought that to me, that was one of my big aha moments as I was looking at science. That number that we knew to be the speed of light in a vacuum came from two constants that had absolutely nothing to do with electromagnetic radiation. They both had things to do with calculating the strength of electric fields around stationary charges, or calculating the magnetic field around a wire that has some current going in it. That's what we use the permittivity of free space and the permeability of free space for. And all of a sudden, those two numbers come together to predict how fast light moves, how fast electromagnetic radiation moves. Okay, so anyway, I guess where I'm going with this is, if I know this number, because it's light or an electromagnetic radiation, and I know this number from what I just told you, velocity is equal to omega over K. And so if I want to find the wave number, I can go, well, K is equal to the velocity, which we give this, it's such a special velocity, we give it its own symbol, C. Why? I have no idea why we picked C. Got nothing. But we do know that it's true. That's the symbol people use. I didn't do it. But if I want to find K, I guess it would be that angular frequency divided by the speed of light. So I guess it's 9 pi. I hope these numbers are doable. Yeah, I can times 10 to the 8th. I can do these almost in my head. Times 10 to the 8th. That's radians, not meters, radians per second. And in the denominator here, that's 3 times 10 to the 8th. And you can hopefully see mathematically, without going to your calculator, what's going to happen here. Okay, meters per second. Wow, that's getting sloppy. There we go. Meter per second. The per seconds cancel, don't they? And radian is nothing. So this has units of per meter. Okay, and let's see, 10 to the 8th cancels a 10 to the 8th there. 9 divided by 3, this looks like 3 pi. And I guess it's radians per meter if you like. And that's fine. But remember, we said about radians, said this multiple times, it's what I call a placeholder unit. All it's doing is holding something in the numerator. Some people like to write this like this, inverse meters or 1 over meters, and you're not wrong. You're fine with that. Just remember, make sure your calculator's in radians. That's the only reason you might be thinking about writing that. So that's what the wave number is, okay? And of course, out of that, I can go, well, if K is equal to 3 pi radians per meter, and that's equal to 2 pi over the wavelength. If I'm solving for the wavelength, I guess it must be, let's see, the pi is going to cancel, right? I'll kind of fracture my equation right there. This is the part I'm working on here. And so I guess the wavelength must be 2 divided by 3. I just brought that over the other side of the equation. I exchanged the means, I guess, as opposed to the extremes here. I exchanged those two guys, and my wavelength is 2/3 of a meter. Okay, and that's kind of an important step. You can go for other parameters if you want. I gave you omega here in radians per second. The other way we talk about frequency. We don't have the omega, which only has units of radians per second. We want frequency, which has units, remember, of hertz. A little bit of review from back early on in the semester. That's a cycle per second. Well, there's 2 pi radians in every cycle. So in order to get the frequency, it really is just a unit conversion. I've got radians per second divided by 2 pi radians in a cycle, and that gets me to cycles per second. And so I suppose if I've got 9 pi times 10 to the 8th radians per second, and you divide by 2 pi, I guess what's that, 4.5 then? Pi cancels, so it'd be 4.5 Yeah, times 10 to the 8th hertz. And you can see why metric prefixes come into play here, right? And we don't like writing times 10 to the 8th, okay? But mega is 10 to the 6th, right? So if I make this, it'd be 10 to the second left over, turn that into megahertz, right? And so now I've got 450 megahertz. And that's just a little bit of unit review, which hopefully doesn't bug anybody at this point in a physics course. And so that's why we like writing things like this. You don't have to. It just cleans things up and makes writing an answer. If you got to type it into a document, it makes it a whole lot easier to write 450 megahertz. Okay. And of course, I took the reciprocal of that. I would get the period. And I think we're done though. Any questions on that problem? You're going to see a similar problem. Instead of starting with a magnetic field, though, on today's worksheet, you'll be starting with an electric field. But you do exactly the same thing. It's an important problem. It was an important problem back when we were talking about mechanical waves on a string and the like, and it's still an important problem here. Questions? Everybody got the units? All right, everybody's awake, right? 10 people out there. Hopefully everybody else is watching the video. All right, move on then. So there, as we said, the speed, I probably could have put this afterwards. Here's one of the most interesting plots I think comes out of all of this. I said that light is a special case. And what you notice about this plot is on the top, this plot shows wavelength, and I guess wavelength is getting smaller. Okay, so it's like kilometers, 30 kilometers right here, and 10 to the minus 12. That's a pico, right? Picometers down here. So this is the size of things like an atom is 10 to the minus 10th. You know, that's the size of an atom right there. Okay, so when you get wavelengths that are about the size of an atom, you're right about there. I mean, this is like running a 10-kilometer or running a marathon. That's those distances, right? Out there, marathon. Am I spelling it right? Okay, and plotted against that at the bottom is frequency, right? Okay, so we know how big the wavelength is, and they're related, right? You can't have, as I said, can't have a wavelength and a frequency that are just whatever you want. As soon as you pick the wavelength, there is a defined frequency because they're related right here, okay? The speed of the medium, the speed of light in a vacuum in this case, is what determines what the other one must be. So if I know what the wavelength is, the frequency is fixed. And of course, if you look here, frequency is going from something fairly slow, like around 100 hertz, up to things that I can't even imagine, 10 to the 20 cycles per second, how fast that must be. Okay, think about the period of that guy. Okay, and things we see daily. By the way, the reason radio waves kind of are in this range, see there's 3 meters right there, that I guess would be 300 meters. You know, we could build antennas, and you have to make the full wavelength, but an antenna has to be usually a quarter of a wavelength is the way an antenna is built. And that's a course for another day if you want to be an electrical engineer and talk about how to transmit electromagnetic radiation and learn about antenna theory. You'll find often it's a quarter of a wavelength. So, you know, that's why radio waves are in that range, because that's the size, that's the range that we can we can actually build antennas. Now, some of you may think, what's this? You're building a couple 100-meter long antennas? And the answer is, yeah, we do. Come on to Annapolis, right on the tip of Greenberry Point, you'll see some huge antennas. And what you also don't necessarily see, because they've taken some of it down, but there were these long wires that would stretch from one antenna to the other antenna, which were literally hundreds of meters long. Those were once upon a time, back in my day when I was doing submarining in the 80s, that was transmitting out to our submarines with very low frequency stuff and really long wavelengths. There was even an antenna array built somewhere in the Wisconsin farm fields where they stretched out horizontally rather than vertically a really long antenna. Okay, so these things do exist. Long antennas do exist. Microwaves, you know, that's what heats your food up. We also use it to do communications from tower to tower, for example. Things that are coming out of fashion, AM and FM radio, and when TV used to be a broadcast thing rather than something that came over to cable, that was the frequencies that your tuner had to be able to catch off your antenna and play on your television set. Cell phones are in this range, and then there's some stuff that we see infrared. Okay, that's, you know, we always associate that with heat. when I was first graduated from the Naval Academy, I went to work at a place called the Naval Surface Weapons Center. It was at the time in White Oak, Maryland. It also had a larger campus down in Dahlgren, Virginia. It's all moved to Dahlgren now. The White Oak campus where I worked is canceled. But we were working on a very rudimentary infrared detection system in the early 80s. Literally, you had to cryogenically cool the detectors, and we only had a couple of ray elements because they were so expensive. And of course, now we don't have to cryogenically cool that stuff anymore. And you can literally buy an infrared camera. You want to see how much heat is leaking from your house. Some company will come and take a picture of it, with an IR spectrum camera, and you'll be able to see where all the heat is being lost at your house in the wintertime. Okay, so those things exist. And just over my lifetime, the infrared imaging technology has changed immensely. Ultraviolet rays came into the media yesterday, didn't they? Because somebody, a scientist from Homeland Security, figured out that this spectrum right here, that ultraviolet spectrum, reduces the lifetime of the coronavirus, doesn't it? So this range of light, and it naturally comes from the sun. You can't do anything about it. It's what gives you a sunburn. Okay. It also, apparently the coronavirus doesn't like that ultraviolet rays. Above that, when you go to the doc and you got to see what happened to your arm or what happened to your leg because you hurt it, you take an x-ray. You can see the difference in density of the materials with x-rays because it transmits through some more than others, and you can able to image that. Gamma rays, ran into those when I was operating nuclear power plants on the submarines. That's what comes out of nuclear reactions, often high energy electromagnetic radiation. Very damaging. Okay, this is the kind of stuff you want to monitor for because it can certainly damage your skin. It's what caused a lot of people to die from the Chernobyl accidents and other accidents of that. It was the gamma radiation they were exposed to. But I skipped right over the most probably important part for us as human beings, and that's the visible light spectrum. Okay, and we associate it with color because we have an optic sensor, okay, an optic sensor, our eye, that happens to be sensitive to that range of the electromagnetic spectrum, which is known as visible light. There's nothing special about light as compared to radio waves or gamma rays or x-rays. It's just electromagnetic radiation. It's an electric and a magnetic field feeding off of each other, but we've evolved over time with our optical sensor to see that range. And if you think about it, why have we evolved as biological creatures to be able to have an optic sensor, a visible sensor sensitive to that? It's because our sun emits radiation that's right about there, right? That's where the sun emits. And since that hits our world constantly, half the day at least, right? Our optic sensor has developed sensitivity to that range of the electromagnetic spectrum. One of my favorite science fiction movies, although I'm not an Arnold Schwarzenegger fan, is Predator. And if you remember right, in Predator, the creature that comes, I guess, to Earth that Schwarzenegger's fighting against, you would often see that it had the ability to see here in the infrared region. And of course, that's sounds like a reasonable theory to me. Wherever that predator creature came from, its sun, not all suns emit that color right there. Other suns have other colors, some emit in the infrared region. And so that predator creature, its eye evolved to see in this range. And of course, when it was fighting Arnold Schwarzenegger, this predator was able to see Arnold because of his body temperature, 98.6, as opposed to all the background stuff that Arnold was running through. And so he was able to detect Arnold's presence in the woods, even though Arnold couldn't see him because he saw his infrared spectrum. And so, it's a reasonable science fiction leap, I think, that if we ever were to meet people from another planet, from another solar system, that their optic sensor, if they have one, would not be exactly like ours. Of course, there's no reason to believe that they have an optic sensor at all, but if they did, it might not necessarily be able to see the same portion of the electromagnetic spectrum that we do. I think, it's funny, if you have any scientific reservations about theory of evolution, I think this is one piece of data that would support the theory of evolution. Of course, there are other people that think that's not true, but why did our optic sensor over time adapt to be exactly the same range of frequencies that our sun emits. Okay, and it's not equal in distribution. It looks something like that, but the peak wavelength that our sun emits is right there in the yellow, and we see that, and that's the way it is. Any questions about that electromagnetic spectrum? All right, moving on. I do want to take another look at the magnitudes of the magnetic and the electric field. A little bit more calculus here for you this morning because it's good for your soul. These two amplitudes right here, because we're going to be talking about energy here in a second. And I want to go back. This is the differential form. Let's see, a rate of change of magnetic field in time. If I multiply that by an area, that's magnetic flux in time. So this must be the derivative form of Faraday's law that I worked up the other day. Okay, and if we believe that these two things are related, and I can write electromagnetic waves as either an electric field, that's this kind of reddish orange piece that's oriented in my y direction, or a magnetic field that's in the z direction, that's in phase with it. These two things are exactly the same at any point in time, at any point in space. Okay, the zeros are exactly the same, the maximums are exactly the same. Then I should be able to take this guy, and I don't know why I wrote them in this order, put this guy right in there after taking a time derivative, and put that guy right there after taking a derivative with respect to x, and see what I got. Okay, and so that's what I'm doing on this line right here. I reverse the order, and I'm kind of clueless why I put one on one side of the slide and one on the other. But now I got to take the derivative of this, okay, and I got to take the derivative of this, and according to this, what I call differential form of Faraday's law, okay, because we looked at rate of change of magnetic fields and we got potentials, electromotive forces out of it. So if I look at the differential form of Faraday here, okay, take which one you want to do first. I've already done these, I guess, once today. Derivative sign is the cosine, bring the constant down. Chain rule says out comes that k, because I'm taking a derivative with respect to x. I didn't write these as this kind of notation that the mathematicians like. It really doesn't matter. I just have remembered, keep the time as a constant. That's why I didn't have to take that derivative in the chain rule, right? Same thing over here though. Derivative sign is the cosine. Good to go on that. Brought the constant down. Chain rule this time brings out a minus omega, but I have a minus sign right here in Faraday's law. That's like the Lenz's law, negative sign. This time I'm not going to ignore it because it makes things positive like I want them to. So that's kind of a convenience. But if you look, I can't really cancel those, although people like to say that because they could be zero. But it is true, though, that the electric field, the amplitude, right, that piece right here, the amplitudes is what we're going to be relating right now. The amplitude of the electric field times K has to be equal to the amplitude of the magnetic field times omega, right? And that's an important piece. So if I rearrange that slightly, I get that. I just divided by I divide it by the amplitude of the magnetic field and divide it through by the wave number. And son of a gun, if I don't get omega over k, which is the speed of light, which was these constants. So it appears to me that when an electric field is moving as electromagnetic radiation, that the magnitude of the magnetic field is intimately linked to the magnitude of the electric field. You just can't have any value of electric field and any value of magnetic field. Once you know one, you know the other as well. And so I guess let's go back to this problem right here. Let's see, I knew the magnitude of the magnetic field, right? And we just said electric field over magnetic field is equal to the speed of light. I hope that's what I said. And so if I know that the magnetic field here has an amplitude of 0.005 Tesla, okay, it seems to me that the electric field must have this value. It would just be 3 times 10 to the 8th meters per second times the number of Tesla, 0.005 Tesla. And so what's 3 times 5 would be 15. I dropped this, didn't I? There's an 8 right there. Okay, so 3 times 5 is 15. That's 10 to the 8th, and that's actually 10 to the minus 3rd. So that's times 10 to the 5th, right? And apparently it's a volt per meter or a Newton per Coulomb. Volt per meter is what I'll go with here. If you want to see those units worked out, Think about back when we had the crossed fields, a magnetic field that was this way, and say an electric field that was downward. Okay, so B and E. And we said there was one speed of a particle of a particular charge that would make its way through that unperturbed, undeflected. And it was a ratio of the magnetic and the electric fields, or the electric and the magnetic fields. And we showed that the ratio of an electric to a magnetic field is a meter per second. Okay, and so go back and look at that if you want to see units. All right, moving on here. Okay, so I guess that's an important concept. I'm going to talk for the last couple minutes here about energy in waves. And we had, when we talked about capacitors, these two equations that I think everybody went, "What's he doing with those?" And now they come to use for us. If you remember, we talked about energy. We said there was big U, joules, and for a capacitor, you had an equation like, I don't know, 1/2 Q squared over C, or I've always favored this one. There's a whole bunch of them, because you know that the voltage here divided by the capacitance is a charge, I guess. Did I say that right? Q is nope, I'm sorry. Q is equal to C times V. So I'll just write that. So the charge is equal to that. So you can plug in for the capacitance, plug in for the voltage, and get another energy equation. That was in joules, is though my point. Okay, that's joules. And then we said, well, there's this lowercase u, which is an energy density. That's joules per meter cubed. Okay, now that's when I've got a capacitor, I've got a device. It's finite in extent. There's a fixed number of volts. There's a fixed number of farads that once the manufacturer builds the capacitor, the thing has. So finding total energy sort of makes sense. But for a traveling wave that takes up some range of space, what's your volume going to be? Okay, so that's why for energy in a traveling wave, it makes a whole lot of sense to divide volume out if you can and speak of the energy density. And if you remember, when we were talking about capacitors, we said it was 1/2 the permittivity of free space times the electric field squared. Okay, and I guess was it this week or was it end of last week? We talked about the energy density in an inductor, and it was 1/2, 1 over the permeability of free space times the magnetic field squared. I'm not sure I made you calculate these things, but we did show you those equations. Okay, and so now if I've got electromagnetic radiation, where that's just an E0 times the sine of kx minus omega t, and this guy's exactly the same, only it's a magnetic field amplitude times the sine of kx minus omega t, and I'm going to be too lazy to write that out. Those two will be exactly the same. I guess, what is the energy density? And it seems to me, and this equation might be misleading, and I'll make sure we clear it up here. We just said that, let's see, the magnetic field is equal to the electric field divided by C, right? I think we said that. Go back a slide. Let's make sure I got that right. Yeah, electric field divided by the magnetic field is equal to C. Wrong way. Okay. Electric field divided by magnetic field is C, so I can switch those two around, and that looks right. And what I'm really talking about is the amplitude. Okay. And so let's see. If I want the magnetic field squared here, okay, it looks like that second term would be, and I'm just bringing this guy, I'm not going to rewrite it because it just takes too long with my mouse. Put that guy right there. And now look at what happens here. I got 1/2 times the permeability of free space. And in place of the magnetic field, I'm going to put the electric field squared over C squared. Okay, now remember we said about the speed of light. It is related to these two things. So the speed of light squared must be equal to 1/μ0 epsilon 0. Okay, so that's what I'm going to put right there. I'm going to get rid of that. It's in the denominator, so that means I'm multiplying by μ0 epsilon 0, right? And then that cancels. And look what happens to this second term here. I'll write it now. The first term was 1/2 the permittivity of free space times the electric field squared. The second term, which is the magnetic field's energy density, turns out to be exactly the same, 1/2 the permittivity of free space times the electric field squared. 1/2 plus 1/2 is just 1. I can write the energy density in favor of only the electric field squared, right? And that's why I wrote that. And this, you got to recognize, I'm often talking about the magnitude of this, but then I've also got that sign, which is squared, all hidden in there. So it looks a whole lot simpler than it is. Okay, so be careful. This thing's changing. It's going up and down and up and down and up and down as time elapses. And I could have done exactly the opposite. I could have put in for electric field squared, I guess would have been the speed of light times the magnetic field, right? Could have done that. And I would have found I could have written the energy density favoring only the magnetic field, or I could write the energy density as favoring the electric and the magnetic field, and then I get these constants out front. I could have done that as well. So either only electric field, only magnetic field, and then a mix of the two, and you know, whichever numbers you know will be depending on which one you might use in order to calculate the energy density. All right, now I got to talk about a kind of a interesting vector invented by a guy named John Poynting, spelled with a Y. But it's sort of an interesting pun because the Poynting vector is defined to be 1 over the permeability of free space times the cross product of the electric and magnetic fields that are here. And that's actually a definition. But here's the result of the definition. Take the cross product of any electric field, let's go this one up here, with a magnetic field right there. Let's see, first vector, second vector, my thumb points in the positive x direction, which is the direction that the wave is traveling. So in a kind of an interesting pun, the Poynting vector has as its direction the direction that the wave is traveling. It points in the direction the wave is traveling. And that's as close as you're going to get to humor out of me this morning. All right, so that takes care of, everybody got that? I mean, if you can do the right-hand rule, go any place you see the two, the orientation is perpendicular, like we said, but they stay fixed relative to each other. If the wave is going in a particular direction, E cross B has to be such that the result of E cross B is the direction the wave is moving. Points in the direction the wave goes. All right, now, got it. So you can do that. What about the magnitude? And, you know, when we talked about mechanical waves, I think what we looked at was the amplitude correlating to how loud the sound was. And in fact, we even took the amplitude of a mechanical wave. We talked about the decibels as how loud a wave was. Well, in the case of electromagnetic radiation, particularly the visible type, that amplitude would be, I hope you believe, brightness, how bright a particular source of light is. And although we can't see it, how intense, I guess we might say, the ultraviolet radiation or the infrared radiation or even the radio wave that's coming. How strong is the signal? What's the intensity? But for optics, that becomes brightness, okay, physical brightness. And it should be related to those amplitudes, just like volume, loudness, was related to the mechanical amplitude. And Poynting's vector helps us out with that. And so if I've got the direction, it's the direction the wave's traveling, the magnitude of Poynting's vector is just the magnitude of the electric and the magnetic field, okay? And what I did here, I guess, is I used the fact that the magnetic field is just the electric field divided by the speed of light, right? And so now I've got the electric field squared divided by the speed of light. And remember that I guess, what can I do with this? Let's see. I think if I multiply this by C and I multiply that by C, if I changed it, now I multiplied by 1, right? So that got me to C up in the numerator. What's C squared? It's going to be replaced by 1 over the permeability of free space times the permittivity of free space. Cancels that. And then that's 1 over the permittivity of free space in the denominator, so it moves itself up to the numerator, and I could write that. Now you may go, why'd you bother? Let's just go back a screen, see why I bothered. Look right there. That's two of the three terms I have here, right? Those guys right there, that's what I call the energy density, U. So Poynting's vector is related to the energy per volume multiplied by the speed of light. So a couple facts here, I guess. Poynting vector, the direction gives me the direction the wave moves. Let's see what the units of this are. So this is joules. Okay, that's per meter cubed. And then speed is meter per second. So one of those cancels. And a joule per second, you might remember, or you should remember from Dr. Tech's class, is a watt. And then I've got left per meter squared. And so while you might not be able to identify how much volume an electromagnetic wave takes up, even a beam of a flashlight, you can kind of see a cone or like a cylinder, you might try to estimate what the volume is. When it finally hits something though, you can figure out the area over which it hits. That's something that's a little bit doable, okay? So we talk about the magnitude of Poynting's vector. It gives the energy passing through a unit area in 1 second, the power per area. Units are watts per meter squared. Further, when you take the average value of the Poynting vector, okay, we call that the intensity, which would be like brightness, how intense the electromagnetic radiation is. All right, now where's average? I think if you look, the magnitude of Poynting vector has energy squared. All right, so let's see. So electric field squared. So the electric field is E0 times the sine of that phase thing, which I'm going to be too lazy to write. If I square it, well, that just squares, and this squares. Okay, so I want to kind of plot that. If I take either time or position, I don't care. I usually think of a time average, averaging over time. That's what but I could average over space just as well. If I plotted sine squared of kx minus omega t, I think it would look sort of like this. Remember, sine itself does something like this, right? And if you square it, the negative part comes up and becomes positive. Okay, and so then the question is, this sine squared curve, what's its average? Well, remember, a sine goes from from -1 to 0 to +1. The sine squared goes from 0 to 1, okay? The average would be like right about there, wouldn't it? And remember, averages are related to areas under the curve. If I chop that guy up, would it just fill in right there? If I chop that guy up, would it just fill right there? So taking it and dividing it in two, this sine squared curve, this piece right here, does give me the average, okay? And then I just think about the amplitude. And so what I'll do here is when I want to do the average of this thing, I'll just slap in a factor of 1/2, okay? And then at that point, this really becomes the magnitude of the electric field and the magnitude of the electric field. It becomes this thing squared right here, okay? And so that's how we can calculate this thing we call intensity. It is the average value of the Poynting vector. I do want to point out that if you have a source like a light bulb, this power does spread out to give you watts per meter squared. So whatever power gets emitted from the light bulb, like a 60-watt bulb, think about as it spreads out, this area gets bigger just like that. And so apparently from a point source, the power gets spread out over a bigger and bigger sphere, and so the intensity goes down as 1/r squared. In this example here, where I've got just something moving along a line, I think it stays as a constant. But I think in general, it's expected that things are going to spread out over spheres, and you do expect intensity to go down with distance. All right, last thing I think I'm going to talk about is something called radiation pressure. And so far I think we've stayed with electromagnetic radiation as a wave. But now all of a sudden, I'm going to do something a little bit wacky. And I'm going to try to say, well, do these waves, when they hit these surfaces, like when this wave hits this gray surface that I've just kind of drawn in there, does it exert a pressure? And oddly enough, it does. Okay. And you can almost think about a particle or a wave. This was a ballistic pendulum. I hope you studied this problem with Dr. Tech. In fact, I'm pretty sure you did. I'm pretty sure I worked with you in the lab on it. So this thing comes in and hits the mass. The bullet comes in and hits the mass. The mass gets the bullet gets embedded in the mass and moves up, and you can actually, from that height there, figure out how fast the bullet must have been going. And that used to be a way that I think people got muzzle velocity out of guns back in the 1800s, is to build an apparatus just like this. Okay, but light will do exactly the same thing. It will push on this mass. Now, nowhere near the force, but it should push. And I want to remind you, what is pressure? Pressure is a force divided by an area, right? And I also want to remind you that the way Newton said it, a force is the derivative of momentum with respect to time. And, I got too many P's going on here. This is momentum, lowercase p. This is pressure, uppercase P. I didn't do it. I wish we had different symbols for those, but we don't. Okay. Everybody okay with the fact that the derivative of momentum is force? If not, just think about it. Momentum is mass times velocity. If I take the derivative of that with respect to time, very often, as long as the mass isn't changing, just becomes mass times the derivative of velocity with respect to time, which of course is ma, mass times acceleration. So I've just used Newton's second law, but I thought about the derivative of momentum instead of ma. Okay, so that's all I'm writing here. I want to point out, and for you future physics majors, you'll prove this, but I'm going to state without proof, because Maxwell showed it, some pretty intense math. If you thought Wednesday was bad, wait until you see this one, future physics majors. It's impressive. But you can show that the loss or gain of energy, and I'm thinking of absorption here, so it's lost, it's absorbed by some object, that amount of energy divided by the speed of light gives you a change in the momentum of the light. Okay, wait for it. It's coming if you stay with the physics major, for those of you who are, I guess, freshmen. Okay, any event, so I'm going to put that change in momentum right there. And so all I got to do, I guess, is think about a delta t, and think about a delta t here, right? And I've really got the term that I need right there. It is the change in energy over time, the loss of energy over time from the wave as it hits something. Okay, and I guess I got that out front, and I got that out front. So those are my constants now. Pressure, we call it radiation pressure. That's why it's subscripted with R, is just the rate of change of energy in time. That's power, right? Divided by area. Power divided by area. Magnitude of John Poynting's vector. Intensity. But I still got this speed of light hanging around. And so if the wave is absorbed by, say, this mass here, okay, it feels a radiation pressure that's exactly equal to the intensity, the magnitude of the Poynting vector, divided by the speed of light. Interesting. Okay, and now here's the next question. What if the radiation reflects off the object? And so I guess what would happen to this guy if, instead of embedding in the mass, the bullet came in and bounced back? The change in momentum here would be twice as big as if it just got absorbed, just got sucked up and stuck into the mass. Well, if the change in momentum goes up by a factor of 2, the force goes up by a factor of 2, and the pressure goes up by a factor of 2. So if you got a nice shiny object, okay, a nice shiny object, you should find that the light reflects. On the other hand, if you don't, I'm looking to see if I have a radiometer. I think it's in my office at Dunning Hall. If it absorbs, if the light is kind of hitting a black material, well, you'd expect less pressure on that side. And that, what I'm thinking about is, you may have seen these glass bulbs that have this little foil here with a bunch of flags sitting down off it, and this thing is free to spin, okay? And one side is silvered and one side is black. And if you notice, this thing spins because allegedly the radiation pressure on one side is greater than the radiation pressure on the other side, because one side is reflecting and the other is absorbing. And so the thing should feel a net force. By the way, there is a serious scientific design where you would have the sun shining right here, and you make this humongous sail, and somehow you have maybe, I don't know, like a gondola on a balloon. And as the sun hits this thing, it experiences a very small force, but a force that could be used for propulsion that way. And so this radiation pressure is an important idea. All right, I think I'm done for the day, done for the week. Some interesting manifestations of light as a wave. We'll go on next week to talk about some of the things light does that makes us think it's absolutely a wave, interference, diffraction. We won't be talking about polarization, unfortunately, this semester, and I just don't have the time. And you guys have a great weekend. I'll have office hours set up at about 1:30 today, like I normally do. If there's a better time over the weekend or sometime next week, let me know. I see the same people regularly. I like that. That's great. Love to see a few more. Everybody have a great day. I'm going to stop sharing this with you, and we'll end the class here.